Walk in, somebody being asked what a number is.
Right. So that's what I think about when I think of what is a number. Well, if that's what a number is, what's a numeral? And I think we often get number and numeral confused. Yeah.
Is that like a representation of?
Yeah, exactly. I put it is a symbol used to represent a number, but representation of a number would be fine too. So a symbol used to represent a number. And we use a lot of things to represent numbers. We might just use our normal numbers. You might just say there's 5 desks in a room. We might use that tally method. You know, when you're counting something, you're like, oh, I did it once, twice, 3, 4. I did it 5 times. That's a numeral. Tally method's a numeral. Some people might remember Roman numerals as 5. And we're going to get into more systems later on, and primarily today we'll get into one additional one. But we'll talk about more in 2 days. We'll talk about how the Babylonians counted and how the Mayans actually counted and the symbols that they used. But let's start off with our number system, because before we look at some other number system, we better know how ours works, where it came from, and how we use it. So we're going to start off with the number system we use today was invented by the Hindus in India thousands of years ago. So our system is not brand new by any means. It was brought to Europe around the year 900 by Arab traders. Why do you think it was brought about by traders?
The Silk Road.
Okay. But why would specifically traders bring numbers with them?
Oh.
Yeah.
When they trade goods, they trade cultures.
Not only are they trading cultures, when I trade stuff for you and you give me money in exchange, don't we have to have a common idea of currency and counting? Because if you say, give me 60 sheep and I think 60 is 3, we're going to have a problem, right? So traders often brought, like Mazda said, their culture to other places because they're traveling so far. But primarily, they had to have a common counting system between the cultures they're working with. So that's primarily why they brought it over. It also is a place value system, meaning that even though we just have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, they didn't use our numbers. They didn't use 0, 1. They had other representations for 0, 1, 2, 3. But even though we only have 10 symbols, depending on their place value, it changes the value of that individual symbol. Our system is called the decimal system. So you might hear it as a decimal system. Decimal based on 10. And more affectionately, we call it a base 10 system. Because we have 10 symbols, and as soon as I run through those 10 symbols, we repeat. We repeat and move place values. Like we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then when I get to 10, I repeat 1 and 0. So that's what gives me a base 10 system. Why do you think we use a base 10 system? In other words, why do we only have 10 symbols? It's something very primitive. Why we only have 10 symbols? Yeah.
Because 5 is not enough and 15 is too many.
Because I guess it's not too complicated to remember more.
Oh.
That's okay. Yeah, right? What is very innately human about the number 10?
The symmetries.
What was that? We have 10 fingers. What do you think the very first people did? They went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you had to start over. Base 10 system is based upon the fact that we have 10 fingers. If we had 9 fingers, we'd probably have a base 9 system. If we had 2 fingers, we would just have a base 2 system, because you'd be like a 1, 2, 3, 4, 5, 6. That is so boring. Oh, if you had to do that? But think about it. If we only had 2 fingers, you'd get used to it, right? An alien that has 20 fingers would probably think, well, how ridiculous. You count to 10 and you repeat. We go all the way up to 20 and then we start repeating our symbols, right? It's just how you're trained. We're trained, think base 10. All right, doesn't mean that any other system is easier or harder. In fact, we'll learn that the Babylonians actually used to count by 60s. They'd count up to 60 and then repeat their symbols. The Mayans worked on a really weird system where everything wasn't different. We'll talk about that. So we use base 10 primarily because we have 10 fingers. Because we were born that way. Do other systems exist? Well, I already kind of said other systems exist with different bases. Can anyone think of one big system that's used every day that isn't base 10? In other words, there aren't 10 symbols. Yeah.
Well, it's like 4, 8, 16. I mean, no, you like square the number over and over again. So you get like 1024, 2048.
Yeah, we're talking about like hexadecimal type things. Yeah. What do you got?
Wait, what was your question? 'Cause that kind of.
Oh, what other big system do we use every single day? Right? Letters? Letters, actually, you can use letters as base, and we're going to tomorrow. But I'm thinking of something that uses some other just numbers. Yeah. A clock. Actually, clocks are. Because they use a base 60, because you have 60 seconds, 60 hours. So that's a big one. I'm thinking of another one.
60 hours.
60 hours. 60 minutes in an hour. What's a big one? Yeah. Roman numerals, they use a weird base system. We don't really use those today. Yeah. I'm using something that uses a completely different base right here in my hand.
0 and 1.
0 and 1s. That is binary. Binary only has 2 symbols. 0 and 1. So binary is the big one we still use today. All of those are right, though, that you brought up. I just want to write down binary for a fact, because this is called base 2. It only uses zeros and ones. I can't use any other symbol besides 0 and 1. So on the back side, we're going to get into how it works with just zeros and ones. But until then, let's delve deeper into how our system works first. We're going to need what we're learning here tomorrow. Because tomorrow we're going to learn how we go from one base. So if I give you base 30, how to get back to base 10. But we're just going to start with ours. So since the Hindu Arabic numerals only consist of 10 symbols, powers of 10 become very, very important. Because every time I run out of a symbol, I move that place value to 1, 0, or 2, 0, or 2, 0, 0, or 2, 0, 0, 0, which are all powers of 10. So some example of a power of 10s, I'm sure we all know these. 10 to the 0th power equals 1. 10 to the 1st equals 10. 10 squared equals 100. Let's go dot, dot, dot. No, let's just do 10 to the 3rd. 10 to the 3rd equals 1, 0, 0, 0, and then we can continue from there. All right, so just a real quick rehash of powers to 10. 10 to the 3rd has 3 zeros. So the easiest way to do 10 to a power is just count how many zeros. So I have 1 with 3 zeros, 1, 2, 3. 10 squared is 1 with 2 zeros. 10 to the 1st is 1 with 1 zero, and 1 to the 0 is 1 with 0, 0. So this tells you how many zeros you're going to have. All right, by using exponents, we can write Hindu Arabic numerals in what's called expanded form. This expanded form is what we're going to need to go between base 10 and other bases. So although it seems really easy today, it's going to be a little more difficult tomorrow. So if I have 6, 6, 3, I repeated 6, 6, and 3 could have been repeated too. So the expanded form of this is going to be 6 times 100, because I have 6 100s, plus I have 6 10s, plus I have 3 1s. Well, since we're base 10, I just want to use 10s. I don't want to use hundreds. I don't want to use ones. I don't want to use the thousands. So I'm going to rewrite this as 6 times 10 squared plus 6 times 10 to the first plus 3 times 10 to the 0th. All right, if I have to do 3,407 in this exact same form, we have a 3 times, well, I have 3 thousands, so that's going to be 10 to the third, plus 4 times 10 squared, because 10 squared is 100, so I have 4 100s, plus, now you can either write 0 times 10 to the first to keep track of your values, or you don't have to write this at all. And finally we have plus 7 times 10 to the 0th power. Alright, so that tells me there's 3 thousands, 4 100s, and 7 1s. So we don't have to know how many 10s we are. If we don't put it in there, it just means we have 0 of them. Alright, so that's expanded form. Take a second and write these expanded forms in our traditional Hindu Arabic numeral. Alright, so go the opposite direction with those two. Yeah. What was that?
Do you want us to tell you?
No. Just do them both. I'll put up the answers in a second. Once I feel like everyone has it done or close. All right, first one is 7 times 10 cubed. Well, that'll be 7 thousands. So I have 7,000 something. Well, I have no 100s because I didn't list it, so it's 7,000. I have 5 10s and 4 1s, so you should have came up with 7,054. For the next one, I have 6 with 5 zeros. Well, 5 zeros will be 600,000. So I have 600,000. And I have 8 10s, so it'd be 600,080. Alright, like I said, this might seem easy now, but tomorrow we're going to need this. We're going to need this idea of being able to expand numbers in this manner in order to go from base 10 to base 8 or base 6. Alright, the next part is we're going to talk about binary. And that little section right there is just for you to take any notes you want to. And I'm going to start off with just a little bit of information. So with binary, we only can use zeros and ones. But still I can represent any number I want to. I can write 634 in binary, but just using ones and zeros. So can I get 5 volunteers? I need 5 volunteers. And it's super embarrassing and hard to... No, I'm just kidding. It's not hard to do at all. You're just going to be tools in the front of the classroom. Yeah.
David, you better volunteer.
We got 2.
David, you're volunteering.
I need 3 more. I need 3 more. Super easy, you're a tool.
David.
Yeah.
David, raise it.
Yep, you'll be my tool. Go up here if I raise your hand. Come up. Here. I need 2 more. I need 2 more tools.
I'll give you candy if you do it.
It's not hard, I promise. You're just going to hold something.
I will join
Come
football.
on, David, your buddy.
It's actually more work for the class. Yeah, thank you. Yeah, thank you. Thank you guys.
More work for the class.
Well, you really don't have to do it. You're tools. You're tools. You are my bits. You are my bits of information. You're gonna hold this. Don't turn it around. Don't turn it around. Don't turn it around. Don't turn it around.
That's a 1.
Okay, so we're binary code right now. This is a binary code. What's in front of you right now is 0, 0, 0, 0, 0. If he turns it around, it becomes 1. So that means if I have just 1, if he just turn it around. Turn it around. I'm sorry. Okay. I didn't know. So right now this is just 0, 0, 0, 0, 1, which equals 1. So it turns out in binary, 1 actually equals 1. Now, just like in our system, if I had 5, I could write 0, 0, 0, 0, 5, right? Do we normally write every 0 in front of it?
No.
No. So even though I say it's 0, 0, 0, 0, 1, more often than not, you're just going to write it as 1. 1 equals 1. 1 equals 1. So whenever these turn over, it's either a 1 or a 0. So right now he's got 0, flips it over, it's 1, which happens to equal 1. Now hold on to that for a second. Okay, flip it around. So he's got 1 on his. If Grace turns hers, don't turn yours, hers becomes 1. That would be 1, 0, or 0, 0, 0, 1, 0. What value do you think she has back there? 10? Yeah.
2.
It's 2. Let's see. Turn yours over. So she has 2 there.
It'd be 1, 1.
It would be 1, 0 right now.
You can't write 2, right?
You can't write 2. So in binary, what's in front of you right now is actually 1, 0, which equals 2. Which equals 2.
I get it.
So 1, 0 actually equals 2, because we only can use 1s and 0s. Go ahead and flip yours around. How would I make 3 then in binary?
1, 0, 0.
Say that one.
Is it 1, 0, 0?
1, 0, 0?
1, 0.
Stop. Oh, yeah. What do you got?
Would you have to move like a 0 in front of?
We have to move 0? Not quite. Turn yours around.
I tried, I'm sorry. I'm really bad at my job.
Cheater. Yeah.
0, 0, 1, 0,
1, 0, 0. So that'd be good because his is 1, right? Hers is 2. So it makes sense that hers would be 3. 3 or
4.
4. It could be, let's think about this.
What you laughing at, boy?
Madison, turn yours over. Grace, turn yours over. What if I just have 1, 1? What does it actually equal?
2. No, 4. Right?
No, count it.
3.
2.
If I have 1, 1.
1.
3.
2. Oh, 3.
3.
3.
6.
1, 1.
Where are the dots?
Wait, 11 or?
What? No. Let's not go crazy with this.